Okay, so I'm going to talk about thermal expansion coefficients. And to get there, I want to ask the question, how does the internal energy change when I change temperature under constant pressure? So that would be du dt at constant P. If this was constant V, this would just be the heat capacity, but CV. But because now we're changing temperature, but under constant pressure conditions, I want to know how is the system changing and what is the internal energy. So I start with my total differential. du is equal to how U changes when T changes, constant V multiplied by dt, multiply or adding du dV at constant T dV. Okay, so I want to know how does this whole thing change dt at constant P. So that becomes partial U partial T constant P, and this is now this side, so it's du divided by dt, becomes a partial derivative because the pressure is constant, equals partial U partial T constant V partial T at constant P. So now I'm taking dt and dividing it by dt at constant P. They become partial derivatives, plus partial U partial V constant T partial V partial T at constant P. So this is where that part comes in. So I've got dV dt at constant P, which becomes partial derivative V with respect to T, constant P. Okay. Now you should recognize there's my CV. This is 1. That's glorious. du dV at constant T, well, that's internal pressure. So now I'm left with this is equal to CV plus internal pressure dV dt at constant P. Sweet. And I go back to Atkins. He says, in many cases, partial derivatives have a straightforward physical interpretation, and thermodynamics gets shapeless and difficult only when that interpretation is not kept in sight. So, dV dt, constant P, what does this mean? Well, partial V partial T at constant P represents how much the volume change when you change temperature. So that means as you're adding thermal energy into the system, the volume is going to get bigger. Thermal expansion. So, but the problem is that if you said, okay, I have my coffee and it's going to have a thermal expansion of, say, oh, I'm out of coffee. That's so sad. So my coffee's about right here. And let's say that I go in the microwave and heat it up, and I go and look in the box and the coffee says the thermal expansion for this is 1 liter. Well, I don't even have 1 liter. And does that mean that this is always going to increase by 1 liter? What if I have 20 liters? Does that mean it's 1 liter expansion? What if I have this is like probably 50 mils. What if 50 mils of coffee, there it is, you can see it. What if 50 mils of coffee, does it always expand by 1 liter? So it would be better to have an approximate or a relative metric to know how much is my coffee going to expand when I put it in the microwave or when I add thermal energy via microwaves. Okay, so that means that I want to look then at partial V partial T, how much does the volume change when I change the temperature at constant pressure, divided by how much my original volume was. This gives me a percent change. If I told you that this would change by 1% if you heat it up for every degree, heat it up 20 degrees, cool. Well, I guess it wouldn't be 100, or so if you know that it would expand by 100%, or okay, if it expand by 100%, that would mean my coffee would now be this much. That would be a lot. So you'd want to know in terms of a percentage. That was a horrible example. Okay, anyway, so we define this as the thermal expansion coefficient. And that's equal to alpha. So alpha equals 1 over V partial T at constant P. Such that when I put this back in, this now becomes, so du dt at constant P equals CV plus internal pressure. And now I can solve for partial V partial T this, and it's equal to alpha times V. So here I have now the relationship of how does internal energy change when temperature changes at constant pressure conditions. Heat capacity plus internal pressure plus thermal expansion coefficient times the original volume. Go team. Likewise, I have another coefficient that's called the isothermal compressibility. So in the same way that I derived the thermal expansion, you can also follow a similar path to get to the isothermal compressibility, which is equal to a negative sign 1 over V partial P at constant T. So whereas before I looked at how does the internal energy change under constant pressure if I change temperature, this I'm looking at how does the internal energy change if under constant temperature if I change the pressure. Go team. Okay, and so this thermal expand or this isothermal compressibility, how much does the volume change when you change the pressure? Go team. Okay, so how would you use these? Well, just like the example I did in class. So if KT is equal to minus 1 over V partial P at constant T, let's say I want to know what the isothermal compressibility is for an ideal gas. Well, I know that the volume is equal to nRT over P. So this function right here tells me that what I need to do is I need to see how does the volume change with respect to pressure at constant temperature. Well, that's simply dV dP at constant T is equal to minus nRT over P squared. I've just taken the derivative of my ideal gas law. If this were the van der Waals equation, it would be a little bit more complicated because you'd be taking the derivative of the van der Waals equation and not the ideal gas law. Okay, so then I can just plug this back in and I get minus 1 over V is equal to, whoops, multiplied by minus nRT over P squared. But that's kind of messy. I want to simplify this just a little bit. So nRT, well, that's just equal to PV. That's cool. And my two negatives will cancel out. So I'm left with 1 over V P squared multiplied by PV. Sweet. My pressure cancels out. My volumes cancel out. I'm left with 1 over P. So if I want to know how much does the volume change when I change the pressure of an ideal gas, it changes in the fraction of 1 over P, which should make sense because pressure and volume are inversely proportional. The rate of change of this is going to be inversely proportional to how the other one changes. Go team? Okay, that's all I got. This is isothermal compressibility and thermal expansion.